based on their shape, shearing stress, and compressibility. As you know, solids have definite shape, but fluids, they acquire the shape of the container. Liquids, this is true in case of liquids. Suppose you pour water into the glass, then the liquid will acquire the shape of the glass. So fluids generally, they don't have definite shape. Then what about shearing stress? We have seen in case of solids, suppose you have a block like this, solid block. If you apply a force here, this is called longitudinal force, and this area, suppose this is A, then F upon A will be your longitudinal stress. But solids can withstand horizontal force also. If you apply the force like this is called shearing force. They can withstand shearing stress. But in case of liquids, you cannot apply any horizontal force. They cannot withstand any horizontal force. So there is no question of withstanding shearing stress. Now another factor is compressibility. Solids, we know they are incompressible. Liquids, they are also incompressible. But in case of air, air is a compressible fluid. Like, suppose you have a piston, and here you have oil. Oil is a fluid. If you apply a force, then you can compress this to an extent only. You cannot compress it fully. Ultimately, this liquid will start showing its incompressibility property, and this property is used in mechanical engines. This you will study in your mechanical engineering. So this is about fluids. Now let us see what is density. Density is basically, density is denoted by rho. It is the ratio of mass upon volume. But here, one important fact is there. This mass should be uniformly distributed. Suppose you have a block. If it is a solid block, you can measure its mass and you can measure its volume. This will give you the density correctly. But suppose that block is having some cavity inside. then mass will be less, but it will have the same volume by dimensions if you measure. So in that case, the measurement of density will be wrong. You will have error. So please note that it should be uniformly distributed throughout. In case of liquids also, the same thing is there. Suppose this is the liquid. If you measure its mass and volume, then you can find out the density. What is the unit of density? Density is mass upon volume. That means it is kg upon meter is cube. This is the unit of the density. And what about its dimensions? Dimensions are m, l, minus these are the dimensions of the density. Now density is a vector quantity or scalar quantity. Of course, mass is a scalar, volume is a scalar, so it's a scalar quantity. Now, in case of water, at 4 degree centigrade temperature, the density of water is, it is 1000 kg per meter cube. Now, what about relative density? Relative density is the ratio of the density of any substance with respect to water density. Like density of iron is your 7 kg per meter cube. So its relative density of iron will be 7 point. So relative density is basically dimensionless. Correct. Here, one more thing I would like to tell you, that the density of water remains 1 even if you apply a pressure from 1 atmospheric to 50 atmospheric. This remains almost 1. But in case of air, density of air is almost 1.21 at 1 atmospheric pressure. But if you apply pressure of 50 atmospheric unit, this is at 1 atmospheric unit. 50 atmospheric unit, then this goes up to 60 kg. Means I wanted to show you that air is a compressible fluid. Its density changes with pressure. So I hope the concept of density must have been clear to you. Now we will talk about pressure, which is very important. What do you mean by pressure? We have seen in case of solids, suppose you apply a force like this, and this is the area, then F by A, it is called longitudinal stress. But in case of liquids, you have, suppose one object like this, whose area is A, and if this force is F, then F by A, it is called pressure. At this point or on the face of that object. Now, pressure has got its own property. Like if you have liquid here, if you have a point here, then this P pressure will be same from all the directions. How this pressure is coming on this? Suppose you have an object like this. Then naturally, this pressure is coming. Suppose you have this water column above this face. So the pressure is coming due to the weight of this water column. Correct? So pressure is something like, and pressure, one more thing, it is always normal to the surface. So inside the liquid, definitely object is going to experience some pressure, and that pressure is due to the water column above that. In case of piston, suppose you have oil here, correct? And area of this piston is A, then if you are applying a force F, then what will be the pressure inside at this point? It will be F by A. So in case of fluids, basically, we call it pressure. So pressure, we have formula as P F by A, where F is force, A is area. So force is perpendicular to the area on which this force is there. Naturally, its unit will be Newton per meter square. This is the SI unit. And this Newton per meter square is also called Pascal. It is based on the French scientist Blaise Pascal. In the next video, we are going to see what is Pascal's principle. So unit, and what about its dimension? Dimension is, you can find out, Newton. Newton is your M, L, P minus 2 upon area. Area is your L square. So this will give you M, L minus 1, P minus 2. Correct? Now, this is also very important whether pressure, this physical quantity, is whether this is scalar or vector. But as I told you, pressure can be in any direction. Means it is in all the directions. At any point, pressure is from all the directions, same, it is same. So means there is no distinguished direction for the pressure. So this is a scalar quantity. So this was all about fluid, density and pressure. Now we will see how the fluid behaves when it is at rest. This when it is not moving. On the screen, this is a container and this liquid is there inside this container up to the AB level, and this is open to sky. Naturally, at this level, AB level, it will be atmospheric pressure will be there, and we can denote it as PA. This ABCD block I have taken inside the liquid, which is like this. Here, area is this. We will be talking about this area which is perpendicular to the force. Now at AB level, suppose F1 force is there, and of course at the midpoint of this block, this will be the mass of the or the weight of the liquid, and then at the lower level, BC level, F2 force is acting on this. F2 is nothing but F1 plus mg. F2 is, suppose P2 is the pressure at the level of DC, and P1 is the pressure at the level of AB, then F1 will be P1A and F2 will be P2A, correct? So we can put here P2A is equal to P1A plus what will be the mass of this? Mass is nothing but, suppose density is rho, then density into volume, and what will be volume? Its area is A, and if this AB level is suppose Y1 and BC level is suppose Y2, then what will it? It will become Y2 minus Y1, correct? So that means P2 pressure at DC is nothing but pressure at AB plus rho Y2 minus Y1. We can write it as suppose height of the, or you can take it as Y2 minus Y1. Correct? Suppose AB level is coinciding with this level, then what will be? Your Y1 will become 0, and suppose height of this is h, then we can simply write it as P2 will be nothing but, now here suppose AB level is coinciding with AB, then P1 will become as atmospheric pressure plus rho G H. H is nothing but where this height Y2 minus Y1 is H. When Y1 become 0, then Y2 is nothing but H. So that means at any point H in the container, let us draw another figure. Suppose this is the container This is the liquid level. That means at any point H, at this level, pressure will be what? PA plus rho GH. Atmospheric pressure, because here it is atmospheric pressure plus rho GH. Now, this P2, what is this P2? P2 is called absolute pressure. And P2 minus P0 is equal to nothing but rho GH. And this is called Gauss pressure. And this is what you measure with the instruments. So this proves that the pressure in a fluid is the same for all points at the same level. This is what in the last lecture also I told you. At the same level, if it is at the same level point is there, then the pressure will also be there, will be same. And what about Gauss pressure? Gauss pressure is the difference between the absolute pressure at a point and the atmospheric pressure. Correct? I hope this is clear from you, from this. So our pressure at any point, the Gauss pressure at any point, is simply rho G H. You have to just measure the height and you can find out the pressure, provided you are given the density. In the last lecture, we have seen the difference between gauge pressure and absolute pressure. Now we will see how the pressure can be measured. Torricelli, an Italian scientist, he devised Mercury Parameter. Let us see what this is exactly. What he did, he filled the glass tube. This is the glass tube. We filled the mercury in the glass tube and make it inverted and placed in a trough which is filled with mercury. What he found, that the mercury descended from the top. Naturally here, what will be here? It will be vacuum here because the mercury was filled here, and now when it is inverted, the mercury, this level has descended. And here the pressure is basically zero. He found that mercury had descended and stopped at this level. Naturally, what is this pressure? What is the pressure here? It is the atmospheric pressure. It is sky. This, as if you can say, This atmospheric pressure has forced the mercury up to H height. That means PA, atmospheric pressure, is nothing but rho at GH or H. That is, in case of mercury, it is 13.6 into 10 raised to 3. He found that this H is 76 centimeter or 0.76 meter, and then 9.8 is the gravity. So this is how he calculated, and he found that atmospheric pressure is around 1.01 into 10 raised to 5 Pascal, or we can write it as Newton per meter square. So this is the atmospheric pressure we calculated, and this device was known as Mercury Parameter. Now there is another thing, open tube manometers. What is open tube manometers? Suppose you have a container where gas is there. It is at some pressure, that is P. Then this can be connected to an open tube manometer like this. This is open from here. Naturally, whatever liquid you are filling here, due to pressure from the gas, this liquid will rise. Whatever pressure is there at this in this gas, naturally at this level, same pressure will be there. And suppose this H height is there, through which this liquid has risen. At this P level is here, and here again P, and this pressure P we can equate as rho G H, where rho is the density of the liquid in the open tube, G is usual, and H is the height through which this liquid has been risen. Manometers can be used to find out the density of the liquid. Suppose you have one liquid like this, and it is up to this level. You have another liquid like this, so these levels are same. Suppose this is X, and this is while then you can write down at this level, level O, at this level, pressure will be same. So you can write down here PA plus rho1 G X is equal to PA plus rho2 G Y. PA cancels out, and here you can get a relation between X upon Y will be nothing but rho2 upon rho. So you can measure X and Y. If you know one density of liquid, rho1, rho2 you can find out. So these are the manometers which are used to find out the density of different kind of liquids. Well guys, today we will see what is Pascal's principle. Basically, Pascal's principle states that change in pressure applied on enclosed incompressible fluid is transmitted to every portion of the fluid and to the walls of its container. That means if you have enclosed fluid and externally if you increase the pressure, then that increase will be transmitted to every portion of the fluid, everywhere inside the container. Let us see how we can go about this. You have a container here and there is a liquid inside this. This is enclosed. Now, this container is enclosed by this piston. You can assume this as a piston. And due to this piston, just below the piston, if you have pressure as P external, then what will be the pressure at P, which is a point in the liquid below height H. Pressure at P will be basically P external plus rho G H. I think in this equation there should not be any doubt. Now, if we increase this pressure by delta P externally, we are increasing this pressure by delta P. So now, since your fluid is incompressible, so by increasing this delta P external, there will not be any change in the height H. So what will be the new pressure? New pressure at P, suppose there is an increase, assuming delta P, then this will be P external plus rho GH plus your delta P external, which you have increased. Correct? I think this equation also there is no problem. And this gives you delta P is equal to delta P external. which proves the Pascal's principle that if you have a change in pressure inside an enclosed fluid incompressible, provided the liquid is incompressible, then it is transmitted to every portion of the fluid because delta P is not dependent on H or any other point specifically. It is applicable for every point inside the container. So this proves. Now it has got a very good application that I would like you to explain. This is basically, this system is called hydraulic machine. Now by this piston, suppose you are applying force of F1 and this portion is having the area is A1, then what will be our pressure here? Correct? This is basically, this force is being applied externally. So increase in pressure will be like this. Now as per Pascal's principle, this is transmitted to every point inside the container. So that means this must be equal to, this pressure must be equal to here also, and here suppose you have this force is suppose this one downward, then naturally for balancing this is upward and this area is A2, then this must be equal to F2 upon A2. So this is basically what is this is called output force, and this is called input force. So let us see what is output force. It is nothing but F2 is equal to F1 into A2 upon A1. This is the principle of hydraulic machine. And let me give some numerical values here. Suppose your F1 is 10 Newton and A2 is 4 times A1. This area is bigger, is kept deliberately bigger just to see what happens. Into 4A1 upon, this is giving you 40. So here what is happening? You are applying a lesser force, but you are getting a greater force as an output force. So suppose heavy machinery is there or car is there or anything which is very heavy. If you want to lift, then you can apply the use of this hydraulic machine you can apply a small force and you can lift the bigger heavy weight. Here again, one more thing is there. You are applying a force of F1. Suppose this is down by V1, this piston. Then what will be the volume displaced? It will be A1 into V1. This, the whatever volume you are displacing here, that volume should go up here, and suppose lifting is your, here it is lifted by D2, then what will be, since volume is same, correct? So here D2 is equal to A1 B1 upon A2. So that means with the hydraulic machine, you are applying a smaller force to a greater distance, whereas greater force is being applied for a smaller effect. You are getting a greater force with for a smaller distance. That means work done here will be same. Work done where will be F1 D1 must be equal to F2, correct? So for having the same work done, input work done is same as output work done. With this hydraulic machine, you are going to lift larger or heavier machines. So you can use, so Pascal's principle is basically used for hydraulic machines. In this video, we are going to learn about Archimedes Principle. Before learning Archimedes Principle, let us see here. Here you will find two figures where a block is there, whose area is, face area is A and depth is H, capital H. Now, in this position, it is partially submerged, and in this position, it is fully submerged. When it is partially submerged, then height of H, small h, is underwater. So, in both the cases, if you see, it is displaying some water, and we can calculate that water. When it is partially submerged, it will be rho A and H. This is the, suppose rho is the density of liquid, and here rho S is the density of solid. So rho H is the weight of the or mass of the liquid displaced, and what will be its weight if you multiply it by G. What about the weight of the block? This will be nothing but OS A into H into G. Correct? And what about the weight of water or liquid displaced? This will be nothing but O into A into H into G. Now, when this block is basically in both the positions, the block is in the floating condition. Floating condition. These both are floating conditions. So when it is floating like this, it will experience pressure all around, correct? This horizontal pressure, they will cancel out each other, but the pressure which is coming from the liquid on the lower face of the block, this will give rise to a force, and that is called buoyant force. It will be like this. Here, this will be, here it will be acting. A buoyant force will be acting like this. And mass of the or weight of the block will be like this. Correct? This is called Fg. So if we see like this, here it will be Fb and downward it is Fg. Fg is nothing but here mg you can write, or you can write rho s ah. Correct? What about Fb? Fb is basically buoyant force. The upward thrust is also called upward thrust. This will be nothing but the weight of the liquid displaced, and that is rho a h g. If we take this figure, this is figure number 1, and this is figure number 2. If we take this figure, then for figure number 1, this is your rho a h g. Correct? So what Archimedes experienced, or what is this principle? It says that when a body is fully or partially submerged in a liquid, a buoyant force Fb from the surrounding fluid acts on the body. Correct? This we have seen, the pressure due to the liquid, which will act upward direction. The force directed upward and has a magnitude equal to weight of the fluid that has been displaced by them. So this force, basically Fb, is nothing but, this is equal to the liquid displaced by the block. This is what you have to understand. Here in figure 2, what is the FB? It is rho A H, correct? Because the full height volume of the block we have taken, because block will displace the water equal to its own volume. Now, when FB and FG, when they will be in equilibrium, they will be in equilibrium when FG is equal to FB. This is the equilibrium position, and this is called floating position. So, in a state of floating, this Fg, that is weight of the object, and the buoyant force, that is upward thrust, they must be equal to each other. Then only the object will float. So in both these figures, the object is floating. Correct? So depending on the density and weight of the block, either it will partially float, or it will fully submerged in a state of fully submerged. Correct? Now, what happens when Fg is greater than Fb? Then the object will just go down. You put the object inside the liquid, and it will just go down and go to the bottom of the container or bottom of the lake or whatever it is. Correct? Because here your weight of the object is more than the upward thrust. And when Fg is less than Fb, then of course it will float like this. So this is the equilibrium condition. Suppose any object is there where Fg is less than Fb. You put the object, suppose this is the object. In this object, this condition is there. By some force, you are putting the object here. When you release this object, then in that case, what will happen? It will accelerate in the upward direction till it comes on the surface. So this is all about Archimedes Principle. And here one more thing is there, that is apparent weight or apparent mass. Apparent weight of any body or object in the liquid is equal to actual weight minus your FB. That means when actual weight is actual weight is suppose 10 Newton and FB is 8 Newton. Then the object in the liquid, inside the liquid, it will weigh only 2 Newton. This is the reason you feel the objects heavy in the air. But suppose if you lift that the same object inside the liquid, then you will feel it light because there is a buoyant force from the below, which is adding the lifting. That's why actual lifting becomes less. This is called apparent weight. When actual weight and FD both are equal, actual weight and apparent weight both are equal, then of course your apparent weight will be 0. So a floating body does not have any weight inside the liquid. You will not feel any weight of the object. So this is also very important apparent weight. Correct? So this is all about Archimedes Principle. In this video, we are going to talk about equation of continuity. But before talking about equation of continuity, we have to understand certain other things for understanding equation of continuity, how we can drive this equation of continuity. Here, basically we will be dealing with ideal fluid. Your fluid is ideal. What do you mean by ideal fluid? Ideal fluid means it should have steady flow. Then it should be incompressible fluid. Incompressible flow. And another thing is it should be non-viscous fluid. And another thing is it should be irrotational flow. Means our flow conditions should abide by these 4 laws. Should be steady flow, incompressible flow, non-viscous flow, and irrotational flow. What do we mean by steady flow? Let us take steady flow means suppose a fluid particle is moving like this. You have a pipe. Then at this point, suppose point P is there. At any given point, the velocity of the moving fluid at P does not change with time. Means any fluid particle, if it is coming on this point P, then the velocity should not change. It should remain constant at a given time. like this. Suppose this is another point, then at this point it should have a constant velocity at a given time. So this is called steady flow. Steady flow is also called laminar flow. Means the flow is moving in laminas, in layers. Correct? What about incompressible flow? Incompressible flow means the density of the fluid particles should remain constant. Non-viscous flow means it should not have any friction between the layers. Like one particle is moving like this, another particle is just adjacent to it, it is moving like this. Then they are in close proximity and they should not have any friction in between. Otherwise, flow conditions will change. In practice, it is not so, but ideally, we are assuming that it is a non-viscous flow. Irrotational flow means the fluid particles should not rotate along with the flow. So let us see what it means. Basically, basic important thing is steady flow. Means if every particle is moving in a streamline. These are called streamlines. Suppose this is the pipe. Inside this pipe, these fluid particles are moving in streamlines. So these are called streamlines. Streamlines, according to the shape, streamlines can be like this also. Correct? At any point, tangent to this curve will give you velocity of the fluid particle. So this is a typical streamline. Correct? The flow is moving in laminas. Now, let us see here. Suppose you have some obstacle, then how you can draw the stream. These curves have to be very smooth, and at any point, tangent to the curve will give you the velocity at that point of the streamlines. So this is basically something about streamlines laminar flow, and how an ideal fluid behaves or how an ideal fluid flows. Now, with this concept, let us say, suppose you have an opening like this. This is point P, this is point Q, and this is point R. These are the streamlines going in this pile. So, suppose in delta t time, what will be the mass flow inside this? It will be omega. Sorry, what will be the mass flow? It will be rho. Then area of this, suppose that is AP. Then if velocity is here Vp in delta t time, it is per unit time. This mass will flow up to this distance Vp into delta t. So rho AP into AP into Vp into delta t will give you the mass flow in delta t time through P. Suppose here the density of the liquid is rho P, then it must be equal to, because whatever mass is going inside through this opening, it will reach there at Q point, and it should be the same. Where AQ is the area at Q point, then at Q point VQ is the velocity, and again it is now coming out from R. These all should be equal. So basic idea is whatever mass is going inside, it is coming out. The same thing is coming out from this tube, correct? But since the fluid is incompressible, so rho P must be equal to rho Q and rho R. That means what will be left? AP VP is equal to AP AQ VQ is equal to AR into VR. That means area into velocity. This product remains same at any point in the tube, and this is called equation of continuity. So you can, in simple terms, V1 A1 must be equal to V2 A2. This is your equation of continuity. So product of velocity and area, this remains constant at each point in the pipe or whatever is there where the liquid is flowing. And what is this? A into V, this is nothing but volume flow rate. Now, rho into A into V, what it will be basically? It will be mass flow rate. So, this is our equation of continuity. A into V gives you volume flow rate, means volume flow rate at any point inside the pipe or tube or whatever it is remains constant, and mass flow rate is rho into A into V, that also remains constant. Suppose you have a tube like this, where it is A1, V1, here it is A2. So here you can find out V2 with this equation very easily. So this is the one, this is the meaning of this. I hope you understood this. In this video, we are going to see what is Bernoulli's equation. I have drawn a figure before you. This is basically a water tube or liquid, and a liquid is there, and these are the streamlines. Correct? Now water is flowing inside the tube through this end, and it is coming out from this end. Here at B end, the pressure is P1 and area is A1, and at the E end, the pressure is P2 and area is A2. Now let us consider the liquid lying between B and D. This liquid, it is advancing to C, and here from D to E. In delta T time, this liquid is advancing to C, so that this distance will be, suppose velocity is V1, then it is V1 delta T, means in delta T time, this will advance this distance. Correct? Now the same amount of liquid will come out from D end, it will advance from D, and suppose here at D velocity is V2, then it will be V2 into delta T. Delta T is very small, so it will advance V2 into delta T distance, because we know that delta X upon delta T is basically velocity. So this is the distance we are talking about, V1 delta T and V2 delta T. Now, when it is advancing a distance of V1 delta T at this end, then what will be the work done? Work done is basically force into distance, or you can write it as delta X. Force is nothing but P, pressure into area into delta X. So this is the basically work done at point B. So work done at point B will be your P1. Here A is A1 and delta X is nothing but V1 delta T. Correct? Now what is this? This is the volume of the liquid advancing in time delta T. Correct? So you can say in this fashion that this much work is required for moving the liquid from B to C at Bn. Likewise, at the further end, W2 will be P2 into A2 V2 delta T, or correct, delta V is same because in delta T whatever liquid is advancing, the same is coming out. So in both the cases delta V will be same. So what is the total work done? Total work done will be W1 minus W2, and this we can write it as P1 minus P2 into delta V. Why W1 minus W2? Because W1 is a positive work done, and whereas W2 is the negative work done, because at the farther end, at the output side, the system is doing the work. It is getting the liquid outside. You don't have to do any work. But of course, at the B end, at the initial end, you have to do some work. And basically, this work is being done by the surrounding fluid. Correct? Now, this total work done must bring some change in other energies, because when there is a change, when you are doing some work, then there must be some change in the energies. So what is that change? Basically, one is change in kinetic energy. What will be that? You know, kinetic energy half mv square. Here it will be half rho VT square minus V1 square. This is the change in kinetic energy from end B to end E. Got my point? And of course, there is an elevation also. This tube is rising with respect to ground. Here the height is H1. Here the height is H2. So there will be change in potential energy also. What is that? That is mgh. mgh we can write rho g h2 minus h1 into delta V. This is here also. Delta V will be there because M is what here? Rho into delta V. In MGS also M is what? Rho into delta V. Correct? Now delta V, it will cancel out. And if you rearrange, then what it will give? P1 plus R rho V1 square, this is velocity, plus rho G H1 equal to V2 plus R rho V2 square plus rho G H2. Correct? So, one is this end and two is this end. Correct? So, at one end, P1 plus half rho V1 square plus rho G H1 is equal to P2 plus half rho V2 square plus rho G H2. That means the sum of this remains same. That means we can write it as P is pressure plus half rho V square plus rho G H. This remains constant. Correct? From this equation, this is equal at this point. At this point, that means at all other points, the sum total of pressure plus half rho V square plus rho GH will remain constant. And this is basically Bernoulli's equation. It has got very wide applications. It's very important equation, and this equation has been given by a Swiss physicist, Daniel Bernoulli. Now we will see what is the speed of reflux and what is basically Torricelli's law. Suppose you have a large tank here and liquid is filled up to this height, Y2 height. You have an opening here. If you make an opening, naturally water will start flowing from here. So what will be the speed of this flux? The output water, what speed will be? Suppose this is 0.1 and this is 0.2. Correct? So let us apply Bernoulli's theorem between 0.1 and 0.2. So 0.1, our Bernoulli's equation is basically P plus half rho V square plus rho GH. It is constant. Correct? So at point 1, what is P will be what? Now since water is coming out, so it will be experiencing the atmospheric pressure. So it will be PA plus half rho is the density of the liquid, and suppose V1 is the velocity, this is what we have to find out, plus rho G, and if we take the bottom as a reference line, then rho G Y1 will be this thing. This must be equal to what is 0.2. Here again it is open to sky, so atmospheric pressure will be there, plus half rho. What about V2? Suppose if it is a very large tank, then the surface will be almost at rest. It will not have any velocity. So here the velocity will be 0. Plus, of course, correct. That means this cancels out, and the rho cancels out. So ultimately V1 square will be nothing but two G Y2 minus Y1, or this can be written as 2GH. So V1 is nothing but 2GH. Torricelli also stated that in such cases, the velocity of the efflux will be equivalent to a free falling object, velocity of the free falling object. Suppose you have a ball is there and it is freely falling towards the ground, and suppose height is h, then what will be the velocity? When it reaches here at the ground, it will be nothing but V, suppose V is here, it will be nothing but V root 2GH. So Torricelli also stated, if an object is freely falling in the air, where of course we do not have to take any viscosity effect of the air, then the velocity of the object when it reaches the ground after traversing h distance, it will be root 2GH. And in this case also, water, if it is a very large tank, if you make an opening, then it will have the same kind of velocity. So this is Torricelli's law. In this video, we are going to talk about Venturimeter. Venturimeter is a measuring device, basically. And what it measures the velocity of the incompressible fluids. Suppose you have a pipe, water is flowing through this. These are the streamlines. These streamlines, they never cross each other. Correct? Now you want to find out what is the velocity of the flowing water inside this tube or any liquid inside this tube, what you can do is you attach Venturimeter in between the pipe. Now fluid will be flowing through this like this. In this Venturimeter, one end is broad and this middle portion is constricted. It has got a smaller area. Suppose here at point 1, area is A and point 2, area is small a. And as per continuity equation, we know that V1 A will be nothing but V2. Suppose V1 and V2 velocity at 1 and 2. So naturally, from here, your V2 is A upon A into V1. This is due to continuity equation. Now, we have attached between point 1 and 2, 1 manometer, and we have a fluid here with density M, rho M. This is a broad end, and this at point 2, it is the small, having a small area. Naturally, if you see the continuity equation, velocity at point 1 will be less and at velocity at point 2 will be more because of this equation. But here, let us see what our Bernoulli equation says. Now, since they are at the same level, point 1 and 2, so this potential energy part we can strike off. So with this equation, suppose velocity is more, then naturally pressure will be less there, and velocity is less, pressure will be more. So with this analogy, pressure at point 1 will be more because velocity here is less. And due to this, what it will do? It will apply the pressure in the manometer, and due to this pressure at point 1, pressure is more. So this liquid will rise like this, and suppose this height is h. Then let us see pressure at P1 minus P2, because pressure at 1 is higher. This must be equal to, as per manometer principle, rho m gh, and this must be equal to your half. What is P1? P1 plus half rho V1 square is equal to V2 plus half rho V2 square. Correct? That means V1 minus V2 is nothing but half rho V2 square minus V1 square. And we have this formula. We can replace V2 when half rho V2 is nothing but A upon A square minus 1. You can take V1 square outside. Correct? So this is your, here it will come as R rho A minus 1 V1 square. Correct? So V1, which is the velocity, we have to find out because it will give you the velocity inside the normal pipe through which we have attached the Venturimeter. This will be nothing but square root 2 rho m GH upon rho A upon A minus 1 this this will be and this will be like this. Correct? So this is how we can find out the velocity V1 and this just by attaching the Venturimeter. We know manometer density. Whatever liquid is there inside the manometer density, we know. Density of the fluid in the pipe also we know. We know the area of the Venturimeter one end and other one at the constricted end. So we can find out easily what will be the velocity of the